as we look at the way that igneous rocks melt and what happens when their temperature is raised, because this is a complex process. Imagine the temperature of the rock being raised and the minerals then beginning to melt in the opposite order in which they crystallized. You can well imagine, I think, that the mineral which forms at a high temperature will stay solid longer than the mineral which formed at a low temperature. So in essence, the minerals begin to melt in the opposite order in which they crystallized. That's one aspect of the melting of rocks. Now, when the minerals, in fact, themselves begin to melt, they react together. You can imagine two different beginning to melt minerals reacting with one another. So that's a second point that happens. Now, a third thing that happens has to do with exactly how those minerals melt, and this is perhaps the most difficult thing to understand. Try and imagine a mineral, let's say a crystal of pyroxene, for example, getting hotter. Now, you'll remember that pyroxene, which is an important mineral in basalt, is one of a family of minerals. That is, in some pyroxenes there's a lot of calcium, in other pyroxenes there's a lot of magnesium. And the more calcium you have, the less magnesium you have. The more magnesium you have, the less calcium you have. So that when pyroxene, in fact, begins to melt, what happens is that some of those atoms come out of the pyroxene crystal and other atoms take their place. There's an exchange between calcium and magnesium. So that when that pyroxene begins to melt, the pyroxene crystal itself changes to another member of its family, and at the same time it yields atoms to, if the temperature is gradually rising, it yields atoms to a liquid. So try and have in your mind the picture then of minerals beginning to melt in the reverse order in which they crystallized, that minerals reacting together, and also certain elements coming out of some minerals as the temperature rises and being replaced by other ones. That's all rather difficult to imagine, but let's transfer that to the sites of the igneous activity and just see what happens in actual geological practice, so to speak. The rock of the asthenosphere beneath the site of a splitting ridge, in fact beneath any piece of lithosphere, is this kind of rock that we have here. It's a rather green-looking rock with some brown crystals on it. They're in fact crystals of garnet. The green background is formed of the minerals olivine and pyroxene, and that's the rock that we think makes up the asthenosphere. Let's put those minerals, the garnet, the pyroxene, and the olivine, beneath the diagram there, and see what happens when that rock melts. Garnet, then, is one of the main constituents of the rock of the asthenosphere. The others are, we think, pyroxene and olivine. Now, when that rock of the asthenosphere melts, the process is just as complicated as I described to you a couple of minutes ago. Briefly and simply, what we think happens is that calcium and sodium are released from the pyroxene, and they go to form that part of the liquid which will eventually crystallize as plagioclase. And the sodium and calcium from the pyroxene are accompanied in the liquid by aluminum, which is derived from the beginnings of the melting of the garnet. So that these two minerals, these two, the pyroxene and the garnet, as they begin to melt, contribute to that part of the molten material which will eventually crystallize as plagioclase. The pyroxene, having lost some of its sodium and calcium, when it eventually melts and then crystallizes again, forms a different pyroxene. The olivine, although it doesn't actually behave in detail like this, you can regard as having simply melted and recrystallized again. And these minerals, plagioclase, pyroxene, and olivine, derived from the beginnings of the melting of the asthenosphere, form the rock basalt. And that then is what we think, approximately simplified, happens at a spreading center like this. The asthenosphere begins to melt. About 10% of it probably melts and forms the oceanic lithosphere. Now then, when that basalt goes down a subduction zone, let's take the minerals over here and see what happens to it as it goes down a subduction zone. The olivine, pyroxene, and plagioclase. Without going into detail, what happens then is that sodium and potassium are released from these constituent minerals, and some aluminum and some silica. These are released as the basalt begins to go down a subduction zone, either beneath a continent or beneath another piece of ocean lithosphere. The rock that's then produced is andesite, composed of plagioclase. Let's take these away. Plagioclase and amphibole, essentially. So what we've seen then is we've seen a sort of a one-way street. The creation of oceanic lithosphere by the partial melting of the asthenosphere, producing basalt, and the reprocessing of that basalt to produce andesite, andesite of the volcanic island arcs, or the volcanoes on the margin of a continent. That andesite is this rock. And as well as being light-colored, it's light in weight, and it never sinks again down a subduction zone. Once it's formed as land, it remains land. And looking at that pattern of volcanic activity and, well, volcanic activity at spreading ridges and volcanic activity at subduction zones gives us some hints as to why and how those plates of oceanic lithosphere might move. We get some hints as to the mechanism of plate tectonics. Hot material at the spreading ridges formed into the oceanic lithospheric plates, cooling as it moves away from the, the splitting ridge to the margins of continents, or descending down a subduction zone here, cooling and getting heavier, and perhaps sinking down this subduction zone because it's heavy, but perhaps because it's part of a convection system, getting hotter here, melting, hot, cool, and so on. Part of a convection system like that. That's a second possibility, that the lithosphere is in fact a part of a convection system involving the asthenosphere. Perhaps also the plates move because hot material is squeezed up into here in gaps, pushing those plates apart. Whichever mechanism it is, the oceans are, if you like, the factory for the production of the continents.
Hello, I'm Mike McManus, executive producer in TV Ontario's part-time learning area. Thanks in part to the support of TV